Now, we will talk about matrix notation, matrix and vector notation. So what is a matrix? Matrix, in fact, is just a way of organizing your terms graphically in rows and columns. By convention, we write them in that way that you can see here. It doesn't need to be square. It might be 3 rows and 4 columns. By convention, we put at the first place index of row and at the second place the index of column. So you can see here the 2 is index of column, now the 3 is index of column, 4 is index of column, and here you have 2 is index of row, 3 is index of row. This is the first one is index of row, the second is index of column. But this is just a convention. You can write indexes whatever you want. It's just a convenient convention, nothing obligatory. In mathematics, there is no strict rule what should be elements. Most typically they are real or complex numbers, but nothing stops us to have a matrix of, I don't know, a small house, car, person, and I don't know, a dog or horse or whatever. So in that notation, a house and car are in first row, a person and a horse are in second row. In first column we have a house and a person. In the second column we have car and horse and a horse. It doesn't really matter what we put into the matrix. So obviously matrices can be of arbitrary dimension. By convention, we assign the dimension of matrix as number of rows times number of columns. So that will be the dimension of this matrix, and 2 times 2 is a dimension of this matrix. So obviously a trivial matrix of dimension 1 times 1 is matrix with only one element, and that might be any element that we really want. Right? This is 1 by 1 matrix. Matrix might be 1 by 3, let's say. So that will be 1 row and 3 columns. A1, A2, A3. These are or 3 by 1 And that will be, for example, B1, B2, B3. These are special kind of matrices because we may think about them as vectors. Because usually vectors are tuples of numbers, real numbers or complex numbers. So both of them, row or column, are good representation of vectors. So we will use them as row or column vector. And in fact, about matrices and row and column vectors, this is almost all. But what is special in mathematics about matrices? The special thing about matrices is that we can introduce operations between matrices. What is the simplest operation? That we can have on matrix. So let's take matrix. I don't want to have it very trivial, so let's say I will use matrix 2 by 3. So the most basic operation is obviously adding two matrices, and it is pretty intuitive. What does it mean to add two matrices? We obviously add them element by element. And this is, if you recognize this, exactly the way how we add vectors. So, if we have our two by one matrices, which are column vectors, which we called column vectors, obviously that gives us normal rule of adding vectors. The same for row vectors, why not? Oh, that's not intended. I wanted Y here. So, adding two matrices is a relatively simple thing, but adding matrices is not the most interesting and not the most useful operation that we can do on matrices. The most important operation is matrix multiplication. How do we multiply matrices? First of all, matrices to be multiplied need to have the first one the same length of rows as the second, the same length of column. And once we have that property, we can start with choosing first row of the first matrix and first column of the second matrix, and calculate the first element of outputting matrix as A11 times B11, so first elements of row and column, then second elements plus A12 B21 plus A13 B31. In the next place, there will be still first row from the first matrix, but the second column from the second matrix. So this will be actually A11 B12 plus A12 B22 plus A13 B32. So we have first row of the output matrix. Now, for the second row of output matrix, we take second row of the first matrix and first column of the second matrix. So it's A21 B11 plus A22 B22 B21 plus A23 B31. And the second term of the second row in the output matrix will be the second row of the first matrix and the second column of the second matrix. So that will be A21 B12 plus A22 B31 2, 2 plus A 2, 3 B 3, 2. So this is the rule of matrix multiplication. We are taking rows from the first matrix, columns from the second matrix, and when they conceptually cross, we write a sum of multiplications of elements which are at the same place in the row from the first matrix and column from the second matrix. And that's the whole rule of matrix multiplication. Now, this, what is between elements of inputting matrices, doesn't need to be necessarily multiplication. It might be concatenation, it might be anything. Anything that we denote in a current way, in a current notation, in a current convention, as concatenation of symbols or as a dot between symbols. That's important because later we will use matrix notation not only for numbers but also for operators which will act on something else, on numbers, on functions. Matrix notation will be used to simplify many equations. So you need to remember it is not necessarily that this will be always multiplication. But obviously if we have matrices of real or complex numbers, that will be ordinary multiplication and ordinary summation. So obviously in a particular case of matrix 1 to 1, obviously multiplication is ordinary multiplication of numbers if A and B are numbers. And this is according to the rule because the first row of the first matrix is A and the first column of the second matrix is B. So our resulting matrix will be A, B. So if there are numbers, it will be just A times B. So matrix multiplication in case of matrices 1 by 1 is equivalent to number multiplication. If we take vectors, so if we take column no, I will start with row vector. With row vector. If we take row vector and multiply it by column vector, well, the rule says we take first row from the first matrix and first column from the second matrix, and we multiply relevant elements and add them together. The point is, first matrix has only one row, second matrix has only one column, so result will be either 1 by 1 matrix or simply a number. It doesn't matter too much if that's number or matrix which is 1 by 1. And this is well-known dot product or scalar product, or I think it has a name, inner product. It's a scalar product of two vectors, or dot products of two vectors. There is one more very important operation on matrices, and this is matrix transposition. So let's take a matrix with 2 rows and 3 columns. And if we transpose the matrix, we are replacing columns with rows. So we will have a matrix with 3 rows and 2 columns, and we will take the first column of the first matrix and put it as a row. We will take second column and put it as a row. And we will take third column and put it as a third row. You notice that now we have a different way of notating our indices, but that was never obligatory how we will name objects inside the matrix. It is only the most straightforward way by convention to do this like that. But if matrix is transposed, obviously the elements needs to go where are they places, and they are like that. So this matrix looks like this. In our special case, matrix 1 to 1, obviously nothing changes because row is the same as column. For the matrix which are column row vectors and column vectors, obviously it's transforming one into the other, and obviously transposition of column vector will be row vector. That's why if we have sometimes 2, let's say, column vectors, x and y, we will write their inner product or dot product or scalar product as x transposed multiplied by y in a way that we multiply matrices, and this is scalar product of 2 vectors. And this is in fact everything basic about matrices that we need to know. There is one more operation which is strictly related to transposition, which we will denote as a star. And this simply do a very similar thing than transposition. It transposes the matrix. So now we will take row, column in row, and second column in second row. But also we apply complex conjugate to each element, and this operator, this star operator applied to the matrix, has a name: conjugate transpose.